going to show you how we can solve the exercise from our book. We are going to deal with the exercise 3.32. So the question says, the open loop transfer function of a unity feedback system is given as the following. Gs is equal to k, so this is a constant that we are going to find in this example. And the denominator of the open loop transfer function is s times s plus 5. So here the important part here is the open loop transfer function. So this is not the closed loop overall transfer function. This is just the open loop transfer function. And the question desires a system response to a step input is specified as peak time TP is going to be 2 seconds. So the peak time of the step response will be 2 seconds with an overshoot of 10%. So let's look at our system. So this is the plant, something like a plant, and it is the open loop transfer function. And as I said, this is not the whole closed loop transfer function. For a let's look at the question back. For a unity feedback system, that means there is a feedback with a gain of 1. So that's why we call it unity feedback. For such a system, we have this structure where U is our input here. So this is our input, and Y is our output. So we can also write the Laplace transform version with capital letters. So this is the right way to do it. But for short notation, I'm going to keep capital Y only and capital U only, standing for the Laplace transform of the input and the output respectively. So the question asks for us to design the peak time of the step response. So we will have a step response something like this, okay? And it asks us that the peak time, the time from here to the peak location is TP, is something like 2 seconds. And at the end, the step response will settle down to something, and there must be an overshoot. So this little bump here is the overshoot. Okay, we call it MP, and we want it to be 10%, so that's why we keep it 0.1. So this is important. Do not take it as like 10%. So do not use the number 10, but just take the value 0.1 for your design criteria to be 10%. Okay, TP is given as the pi over omega d. Omega d is the damped frequency. So we can write it more explicitly with the natural frequency. So now we have omega n over 1 minus the damping ratio square. Okay, so this term here is reflecting the damping ratio. So similarly, we have the formula for the overshoot. So that is the exponential function. In the numerator, we have pi damping ratio over in the square root 1 minus damping ratio square. Okay, so we want these to have this specification. So these are the values that we want to keep. So we usually want a peak time to be smaller than a criterion. So let's call it TP star. Here I use the star for desired value. In our case, 2 seconds. So this is in our case 2 seconds. Okay, and the overshoot here must be smaller than 10%. So this is again, so MP desired in this case 0.1. But how do we find this natural frequency of the system or the damping ratio of the system to make our design? So we have to relate this free design parameter K with this specification parameters TP, or more explicit specification parameters natural frequency and the damping ratio. So we have to relate them. In order to do that, we have to first write the closed loop transfer function of the system. So I'm going to write the closed loop transfer function of the system. So I'm just looking here at the node that takes the feedback and makes a difference between the input U. So U minus Y is entering this block here. So I just write the transfer function of the block because everything is in Laplace domain. So I can just multiply whatever I see as a transfer function of that block So that is equal to my output, that is y. So if I leave here the output and input terms alone on each side, I can easily reach to this ratio of the output to the input as k over s squared plus 5s plus k. So this is a form that we like because we know that second order systems, they usually have this structure: s squared plus 2 damping ratio omega ns plus omega n squared. So this is very similar to what I have here for my question. So here I can immediately say that the natural frequency of the system, omega n, is just the square root of k. And from there I can work out the damping ratio easily. So just as I said, the natural frequency of my system is the square root of k. And also I know from the second coefficient of the denominator is 5. So 2 times damping ratio omega n is 5. So from here I can say the damping ratio of my system is 2.5 over square root of k, or the square of the damping ratio in my system is 6.25 over k. So this is something that I would use because I know that the TP, the peak time, it must be smaller than 2 seconds, and with the coefficients that I have here, the TP is just the pi over omega n, right? Sorry, pi over omega d, the damped natural frequency, the damped frequency, that is equal to the natural frequency times 1 minus damping ratio square. So this must be smaller than 2. So now I know, now I can relate this design constraint with the parameters that I have in my system. So what I need to do is I just plug these values into this equation. And so if you do that, we will immediately see that pi over k minus 6.25, they are all square rooted, must be smaller than 2. And this leads the k to be larger than a value something like 8.7. So this is our first decision on this design parameter. So if we choose k to be larger than 8.7, that satisfies that the peak time will be smaller than 2 seconds. Okay, so this is something we find as the first part of the solution. So similarly, we know that the overshoot, MP, that is the exponential minus pi damping ratio. So this is not E, this is damping ratio. So this value, must be smaller than 0.1. So if I took the log of both sides, so from here I get a negative number, so there is a minus sign here, and I have to then multiply both sides by -1. So watch out if you do this simple math trick. It's easy, but usually you can skip this easy point. If you multiply everywhere by -1, you have to invert this smaller term here. So that's a common mistake that we usually do. And from here, if you solve this, and by plugging that the sigma square is 6.25 over k, so if you plug this into that, what you would get is another inequality saying that the k must be smaller than 17.8. Okay, so the first criterion, so here I make a reminder, so the TP must be smaller than 2 seconds, will lead us a k value that is greater than 8.7. So this was the first result, and the second result is coming from the overshoot criterion that tells us that the k must be smaller than 17.8. So the final result is then k must be in the interval of 17.8 and 8.7. Okay, so this is our final result. So if we return to our question, the question A part of the question says, determine whether both specifications can be met simultaneously by selecting the right value of k. So the answer is yes. If I choose my k to be between these values, I can satisfy both specifications. I know that the TP must be smaller than 2 seconds and MP must be 10%. So the question does not explicitly ask us that TP must be smaller than 2 seconds or MP must be smaller than 10%, but from the concept we know that this overshoot is something undesired or the TP is something desired to be very short. So from that we can infer that the design criterion is telling us that the TP must be smaller than 2 seconds and MP must be smaller than 10%. So let's come back to the B part of the question. Sketch the associated region in the S-plane where both specifications are met and indicate what root locations are possible for some likely values of k. So from here we can determine the area in the imaginary plane. So if we say this is our imaginary plane where we put our poles and zeros of the system, so there is obviously this part is the unstable part, but on the left hand side there is some certain area which gives us some parameter region that satisfies this question's desired specifications, that are the maximum overshoot is less than 10% and the peak time is less than 2 seconds. So let's find this area. So what we know at the moment is this k, the k value must be smaller than 17.8 and 8.7. So from here we can easily go to the other. So this is the design parameter. So we can here easily go to the system parameter, the natural frequency. We know that it is the square root of k. So here I can easily say that the natural frequency is between 4.2 and 2.9. Okay, so these are rough values, but I know that this omega n is between these values. So in the complex plane, so this frequency corresponds to the points, okay, that are equally distant. So this, if I plot here a half circle and the radius of the circle is, let's say, 2.9, so this is 2.9. So all the values on this point, so all the poles that are located on this line, they have the natural frequency of 2.9. But in our question we want these poles to be larger than 2.9, so we are interested in the area outside of this circle. So we can draw a similar circle, semicircle. We draw on the stable side. So let's say the new radius is 4.2. So this shaded region are the poles that makes our system having a natural frequency between these two values that matches the design criterion in this question. So as I said, we have to keep the natural frequency in this band here. So if we draw it with a better illustration, as I said, this point corresponds to the 2.9 and this point corresponds to 4.2. So similarly we have the symmetry. So let's concentrate on this side, because whatever we have here is by symmetry is going to be also here. So I'm just filling in this side of the graph. So we are interested in this band here. So all the points in this band satisfies the natural frequency constraint of this question that leads to the k value that we want. Okay, similarly we have another thing that we should look is that is the damping ratio. So we know that our design parameter k is related to the damping ratio. So we can write the same equation here, 6.25 over damping ratio square. So 17.8, 8.7. So I can easily work this inequality out to be 0.59 and 0.85. So simple math trick will give me this interval. That means for these k values, the damping ratio of my system is between these two values. Okay, so on the imaginary axis, the damping ratio, so if we have a pole here, so this must be a straight line, the damping ratio of this pole corresponding system, obviously there is a complex conjugate, but the sine of this angle, okay, the sine theta gives me the damping ratio. Okay, so in other words, this this angle here is the arc sine of the damping ratio that I want. So from these values, I can relate that this angle here must be larger than 36 degrees and 58 degrees. I find these angle values from this relationship. So a pole here has a damping ratio that is graphically the sine of the angle that this pole makes with the imaginary axis. So that's an important point. So for our system, that makes, so this angle must be larger than 36 degrees. So let's say this is 36 degrees and smaller than 58. So there is a region. Okay, so this is 58 degrees, and the answer, so the poles that we want to find must be within this slice. Okay, so similarly, there is a region here and there. This is the between 36 degrees and 58 degrees. So if we also take a nice graph here, so this was the previous finding between 2.9 and 4.2, and now we have another constraint. So this is 36 degrees for the second line, 58 degrees. So the intersection of these two constraints, so this is the natural frequency constraint and this is the damping ratio constraint. We now know that we can only take the values in this region. Okay, we can only take the intersection of these two criteria. So these are the parameters that would give us the design specifications of the question that we are dealing. Okay, so there is a third parameter that we should look at, that is the sigma. So the sigma of this system is basically, so the sigma of the system is basically the natural frequency times the damping ratio. So from the previous two findings that we had, we found that the minimum omega n of the system is 2.9, okay, and the minimum damping ratio of the system can be 0.59. So that means the minimum sigma of the system can be only 1.7. Okay, and the sigma corresponds to, in the complex planes, the sigma corresponds to a line here and the distance from the imaginary axis. So that means our sigma must be greater than 1.7. That gives us the area on the left hand side of this line, where this line crosses the real axis at minus 1.7. So if we look now the intersection of the three regions, so the first region is the omega n region, so the green region is the damping ratio region, and this pink region is the sigma region. So they are dependent variables, but it is always useful to look at the graphical corresponding areas. So as we find for the first two intersections, we are left with these two regions. So all the values that we find here, so if we choose a system to have this pole and this pole, or this pole and this pole, okay, that they will be two different systems, but they will both satisfy the design requirement that the peak time is less than 2 seconds and the overshoot is less than 10%. So they will basically give us two different K values. So we get the maximum oscillation in this system from the point at the top. So for this point here, we get the maximum oscillation. So actually the distance between the real axis and the pole location is giving us the damped oscillation. So we can find the value K here that will correspond to the maximum oscillation.